Hello, everyone. Welcome to the Analog Electronic Technology course. Previously, we've learned how to identify various types of feedback: positive versus negative feedback, AC versus DC feedback, series versus shunt feedback, and voltage versus current feedback. Now, we'll move on to studying the 4 basic configurations of negative feedback amplifiers. As we know, when a feedback network is connected to a circuit, the input side can be configured in either series or shunt mode. On the output side, the feedback signal can be sampled in 2 ways: voltage sampling or current sampling. This gives us 4 possible negative feedback configurations: voltage series, voltage shunt, current series, and current shunt. Note that these 4 configurations generally apply to AC signals. Here is the block diagram of a voltage series negative feedback amplifier. In this circuit, the input loop sums voltages. The instantaneous input voltage VID equals the source voltage VM minus the feedback voltage VF. The output sampling signal is a voltage, which serves to stabilize the output voltage. Therefore, it can be regarded as a voltage-controlled voltage source, typically used for voltage-to-voltage conversion. Hence, it is also called a voltage amplifier. A practical example is this non-inverting amplifier built with an operational amplifier. Using the feedback type and polarity identification methods we discussed earlier, we can determine the configuration of this circuit. Here is the block diagram of a voltage shunt negative feedback amplifier, along with a practical example, an inverting amplifier. The distinguishing feature of voltage shunt negative feedback is that from the input side, the signals are summed in the form of current. The net input current IID equals the source current II minus the feedback current IF. From the output side, the sampled signal is a voltage, which helps stabilize the output voltage. Therefore, it can be regarded as a current-controlled voltage source, typically used for current-to-voltage conversion, and is also known as a transresistance amplifier. Similarly, in a current series negative feedback amplifier, the input summation is in the form of voltage, and the circuit works to stabilize the output current. Since the input is a voltage and the output is a current, it can be regarded as a voltage-controlled current source, commonly used for voltage-to-current conversion, hence also called a transconductance amplifier. A practical example is shown in the diagram. The current shunt negative feedback amplifier is characterized by summing the input in the form of current, with the main function of stabilizing the output current. It can therefore be regarded as a current-controlled current source, commonly used for current-to-current conversion, and is also known as a current amplifier. A practical example is shown in the diagram. Just now, we went over the key features of the 4 negative feedback amplifier configurations. Next, let's look at a few examples to see how to determine a circuit's feedback configuration. First, consider this circuit. It's clear that this circuit uses interstage feedback with a feedback path through RF. Since there is no capacitor in the feedback path, the feedback exists for both AC and DC signals, but we will focus on the AC case here. Let's apply the instantaneous polarity method to determine whether the feedback is negative. Assume the input is positive. The signal enters at the base of T1 and is output at its collector, so the collector signal of T1 is negative. This signal is then fed to the base of T2, while the feedback signal is taken from the emitter of T2 and fed back. Therefore, the feedback signal is negative, and when it is passed through RF back to the input, it remains negative. Because the feedback signal and the input signal appear at the same terminal, the net input decreases when they are combined, indicating negative feedback. From the input side's perspective, since both the input and feedback signals are connected to the same terminal, the feedback is shunt feedback. Next, let's determine from the output side whether the feedback is voltage or current feedback. If we short-circuit the load, it is clear that the feedback signal VF is not zero. Therefore, this is current feedback. Thus, this circuit employs interstage current shunt negative feedback. Now, let's look at another circuit. Here, the signal is amplified in two stages, first by an op-amp, and then by a BJT, before being sent to the output. The output signal is fed back through a feedback network formed by R1 and R2 to the inverting input of the op-amp, meaning interstage feedback is present. First, we need to determine whether this feedback is positive or negative. We'll again use the instantaneous polarity method. Assume the input signal is positive. Since it enters the non-inverting input of the first stage op-amp, the first stage output will also be positive. This output is then applied to the base of the second stage BJT, so the base is positive as well. The signal is then taken from the emitter of the BJT and fed back. The emitter is in phase with the base, so it is also positive. Passing through the feedback network, the feedback signal that reaches the op-amp's inverting input is still positive. The op-amp's net input is the difference between the voltages at its two input terminals. With feedback applied, the net input decreases, so the feedback is negative feedback. From the input side, because the feedback signal and the input signal are connected to different terminals, the feedback is series feedback. From the output side, if we short the output terminal to ground, the feedback network is bypassed, making the feedback signal VF equal to 0. Therefore, this is voltage feedback. The circuit employs interstage voltage, series negative feedback. Now, let's examine another circuit, one we have analyzed before. This circuit contains two interstage feedback paths. The upper path provides DC feedback, while the lower path provides both AC and DC feedback. As we mentioned earlier, the four basic feedback configurations are usually discussed in the context of AC signals, so here we will focus only on the AC feedback in the lower path. We again use the instantaneous polarity method to determine whether the feedback is positive or negative. Assume the input signal is positive. The signal enters at the base of T1 and exits from its collector, so the collector output of T1 is negative. It then enters the base of T2 and exits from its collector, making the output of T2 positive. Finally, the signal enters the base of T3 and is fed back from its emitter, so the emitter is positive. The feedback signal, returning via the feedback path to the emitter of T1, is also positive. Since the net input decreases, this is negative feedback. From the input side, because the input signal and the feedback signal are connected to different terminals, this is series feedback. From the output side, if the output terminal is shorted, i.e., VO is grounded and equals 0, the emitter current of T3 is still controlled by its base current, so it continues to flow. This means the feedback signal VF is not 0, indicating current feedback. Therefore, this circuit employs interstage current, series negative feedback. Finally, let's look at this last circuit. This is a two-stage amplifier, similar to the ones we analyzed earlier, and it also uses interstage feedback. The feedback path here is simply a single wire. Using the instantaneous polarity method, it's easy to confirm that this is a negative feedback circuit. The exact polarity relationships are shown in the diagram. Since the output signal VO is fed back through the wire to the source of T1, while the input signal enters through the gate of T1, the feedback signal and input signal are applied to different terminals, making it series feedback. From the output side, if the output terminal is shorted, the feedback signal VF becomes equal to VO, which is 0, indicating voltage feedback. Thus, this circuit employs interstage voltage series negative feedback. In this lesson, we have gained a solid understanding of the four basic configurations of negative feedback amplifiers, their characteristics, their effects on circuits, and the methods for identifying them. Let's wrap up with a brief summary. Based on the different ways the feedback network connects to the input and output terminals, we can form four fundamental configurations of negative feedback amplifiers. 1. Voltage series negative feedback. At the input, the signals are summed in the form of voltage. This configuration stabilizes the output voltage and is used for voltage-to-voltage conversion. 2. Voltage shunt negative feedback. At the input, the signals are summed in the form of current. This configuration also stabilizes the output voltage and is used for current-to-voltage conversion. 3. Current series negative feedback. At the input, the signals are summed in the form of voltage. This configuration stabilizes the output current and is used for voltage-to-current conversion. 4. Current parallel negative feedback. At the input, the signals are summed in the form of current. This configuration stabilizes the output current and is used for current-to-current conversion. That concludes our lesson on the four basic configurations of negative feedback amplifiers. Thanks for watching.